Good morning or good afternoon, depending on the time of the day that you guys watch this webinar. The title of this webinar is When Do We Need Dynamic Stability Studies, Examples and Arc Flash Calculations. Let me just start with introducing myself. My name is Afshin Majd. I manage our my title is Director of Engineering Department. I manage our engineering department and technical support department, and very much I have been in charge of dynamic stability and harmonics module for the past year and a half. So I used some of the feedback that I have got from our users, sometimes people who are not our users necessarily, but have been looking at our product or have been looking for something that matches the applications or questions that they have, and I put everything in one presentation, which is going to take probably 1 hour. And I start with the introduction. I'll go with some real life examples that we will need to use dynamic stability module. Then I'll go a little bit deeper and I'll present a few examples of how we can use dynamic stability in real life. And then after that, I would also talk about different parameters that you might need when it comes to dynamic stability modeling, and in terms of the different components, what would be needed to do a good modeling in dynamic stability. So going back to the topic of the presentation again, when do we need dynamic stability studies, and some examples. One of the examples that we will be looking at has some arc flash outputs in it, and basically the module itself is capable of performing arc flash studies. The question that will come up right here is that some people might ask, well, you have short circuit or you have other modules that they also perform arc flash calculations. What's the difference? So here I'll briefly talk about the differences that we also have when we do the dynamic stability modeling, and then the arc flash results that come out of dynamic stability. So let me just go to the second slide here, and let's start with some introduction. The presentation goes, the whole objective of this presentation is that, number one, dynamic stability is a module that it's designed for a very special type of applications. I wouldn't encourage or I wouldn't recommend application of dynamic stability for any type of a study, but it happens to be a type of module or a study focus that comes into applications when there are little bit more sophisticated type of analysis are involved, and there is a little bit more data gathering involved, and the results that come out of this module are not again necessarily applicable to any type of a study, but the type of studies that we use dynamic stability for, we have to be very, very careful in terms of what type of data we need, how we put them in, and how we interpret the results that come out of the dynamic stability. In terms of the users, I would say that we don't have a whole lot of users that use dynamic stability, but those who do tend to be users who do more specialized type of studies, and that's the feedback that I get. And usually the classes that I teach or the type of people that I interact with regarding this module, I found them people who have done a lot more study work, and they're more, I would say, they get involved with a little bit more complicated problems. I mean, that's the best way of putting it. The very big difference of dynamic stability module that I can just mention over any other type of module that we have is that there is a time dimension in here. There is a reference to time, which means that we are looking at the waveforms and change of waveforms over the time. That would be the very first issue that I need to mention here. But let me just go very briefly in 2 slides over the objectives that I'm trying to follow here, the points I'm trying to make here, and then I'll go back and then I'll go a little bit maybe more in detail. I'll talk a little bit more in detail about what is the main difference, why, what type of people, what type of application, what cases we need to go and utilize this module. So in terms of objectives, we like to expose the participant to dynamic simulation principles. We would like to uncover the simplicity in dynamic simulations, even though, as I mentioned, it's not necessarily the easiest module to learn, but like anything else in a study world, it takes a little bit more to learn and it takes a little bit more to get familiar with, but the advantages are just much bigger than, in terms of dimension compared to the effort and time that you have to put in order to learn the module. When you figure out, or when you are confident that this is the application, this is the case that you need to use the module, and you use the module, if you learn it very well, you will see that almost no other study focus can provide the results that you want. So even though, again, it might be applicable to more sophisticated cases, it's not that difficult to learn. And we will see that, end of this 1 hour presentation, we will see, after performing a few examples, that it could be quite user-friendly. It can be quite easy to learn. However, when you learn it, it has a lot of applications. We will try to create a healthy attitude of questioning results. This is not limited to dynamic stability. I would say any other module that you run, given power flow, given short circuit, given any other type of module that you run, you always question the results. We develop a software. We are very happy to have a very large database, I would say a very large a group of companies, individuals, people who use our software and provide data to us. But we always mention that this is a tool, and you always have to be able to utilize the tool in a proper way. So you need to know why you use it, what type of results you expect, and you always have to have a way to verify and question the results. So, and we always welcome that type of questions. We get questions all the time about our short circuit, about our load flow, and obviously when it comes to dynamic stability, because the type of studies, we might get a little bit more complicated, a little bit more difficult type of questions, but we always welcome that. Learn methods to perform induction motor parameter derivation. That's something that I will cover, but it's not going to be covered in this presentation. So I will have a series of presentations that come right after this one during it, I would say during the next 2-3 months, and then eventually there would be a class, there would be a harmonics and dynamic stability class in Portland, which is around end of October. In fact, it's October 31st to November 4th, and the more details are on our website that you can go and see there. And then end of the presentation, I will provide more details on that one too. Now, in terms of the goals that we are following here, we try to learn methods to perform induction motor and synchronous motor starting simulations. We try to learn how to select the best models for your installed equipment, learn how to define parameters for models and enter data into your EasyPower database, learn how to critique induction motor and synchronous motor data supplied by manufacturers. So, just going back to the last item that I covered here, if you notice, learn methods to perform induction motor parameter derivation. This is a software. In fact, this is a tool built into dynamic stability module. And as we speak here, let me just open up our EasyPower. Again, we are still just beginning the presentation, but I just wanted to show you the dynamic stability icon here. So this is our database edit. You go to dynamic stability. Obviously, you see the plot, the screen changes. There would be a plot section that you can see the plots. Here is, the one line, the way that you can see one line in other modules. The results show up here. As soon as you switch to dynamic stability, you would immediately see a initial power flow results on the screen, which again, one of the things that really distinguishes, one of the things that make it, the dynamic stability stand out among all different modules that we have, is that it goes in every step of the work. It goes and checks the results and gets the results from the power flow module, and then goes through different states, solves a lot of differential equations, and goes to the next step. But I leave it right there. This is the screen for our dynamic stability module. This is where you would see all the logs and results. This is where you see all the plots. And again, you will see a lot of power flow options available here, because again, for very obvious reasons, that every step of the work, a power flow simulation is being run here. So this is the module. This is the icon. That's after you input all the information, you would go and switch to dynamic stability. And again, in a few minutes, I'll show you how you would need to put the data in this module. Now, learn how to define parameters for models and enter data into your EasyPower database, learn how to critique induction and synchronous motor data supplied by manufacturers, which we talked about it briefly. We also learned how to specify plot channels for viewing dynamic simulation results. So there would be plots, as you see here again, that you can plot them, almost similar to our harmonics module. When you double click, and again I can just talk about them maybe a little bit more in detail, but when you double click on bus or a breaker, you would see that some actions would be happening, and when those actions happen, we have an auto plot capability here, which means that we will be plotting some of the parameters here for dynamic stability. So let me just go back here. Review the extensive set of data supplied in the user library. Learn how to create new dynamic model entries in user library. Review each model supplied in EasyPower Dynamics. Learn how to perform detailed dynamic simulations using a script. So this is another type of work that can be done in dynamic stability. And as I'm going through all these different options here, let me just briefly, before we go to application of the dynamic stability here, the next slide, there are two different type of simulations that we can perform in dynamic stability. Obviously, this is the database edit mode. If you want to go to dynamic stability module, switch to dynamic stability module here, you would go to DS options here, and you can define all the, so now you would see that all the dynamic stability options are in here. Obviously, these are some of the options that you can use in order to optimize or in order to change the results that you would see on the screen. I'll go over them very briefly. In the next series, maybe little by little, I'll show that turning on or off any of these options, how it's going to impact the output results of dynamic stability. Simulation time step, obviously, is the time step that the software uses to progress from one step to the second step. Step run delta time. This is an option that, again, it's an interesting option that I'll give you brief explanation, but we can certainly do more examples when I get there. You see this green run button here, and this green run button has a capability of kind of running the simulation, and then instead of seeing the whole waveform, it allows you to plot the waveform in these time steps that you define them here. For example, if you say 0.1 second here, you can just click on this run, and it runs the entire simulation for you. And maybe I can, even though I understand it might be a little bit short, but let's just give it a try here. Let's say you have one script here and you run it. Let me just go here, go to here, steady state, edit. It just runs. And let me open up another example here. And one good example would be the one that I was just about to show middle of this presentation here, but I'll go and pick it from here. Maybe I would say let's pick this example here. Go to dynamic stability, steady state, script. If we have anything, well, we don't have anything here. Let me just go and define an event here, and for that event I would say first run to 1 second, then maybe open one of the breakers. Let's do this one. Let's go and open one breaker, LV breaker, and that is BL2. And so when we open it, then I go and we would say run for 4 seconds. So what it means, we will look at it in more details. What it means is that we run the simulation for 1 second, we will open LV breaker BL2 and we run for another 4 seconds after that. So I would say okay, I would say close, and I would go here and I would run the simulation. The results are going to show here. As you see, in fact the BL2 that I chose was this breaker here, and you know, the breaker opens. Obviously there are a lot of waveforms that I talked about, and I mentioned that you can see the waveforms based on time. As you can see here, as time progresses you can see the differences. That's one of the biggest differences of the dynamic stability module versus other modules in our program, that you can see the differences. You can see the change in the waveform when an event, a transient event, happens in your system. That transient event could be a wide range of different events that you can define. You can define a fault, you can put a fault on a bus, remove that fault, you can close a breaker, you can open a breaker, you can step change in the governor of a generator, you can start a motor, you can do all those things. And the fact that the waveforms look like this is that you have to go, and in a step you have to go and define dynamic stability models for each module. So going one step back, looking at the fact that why do we need to use dynamic stability module, because short circuit, load flow, and let's say protective device coordination, they all are sort of a snapshot of what happens in your system. I mean, starting from your load flow, you put in all the values for your load flow, you run the system. There is no mention of time. What happens is that it's very much a simulation of a system that you have, let's say 10 gigawatt or 10 megawatt or 10 kilowatt generation, 5 kilowatt consumption of load somewhere else, somewhere in the system, 3 kilowatt somewhere else, and then you run the system. The assumption is that the system and EasyPower, load flow module of EasyPower, is going to solve this system for you, give you all the currents, give you all the voltages, give you all the power and reactive power, and everything is going to be given out in terms of reports or displayed on the screen. Those are the values after the system completely settles down. In other words, it means that the system will go and find a steady state point, and that steady state point is what you see as the final result. Now, the question that I would pose to any user that uses those type of studies is that really the final results that we want? Sometimes the answer is yes. Sometimes even we don't know, but the answer might be maybe not. Let me just give you another example. If you look at, let's say, breaker ratings, bunch of different reasons. When you look at the breaker rating, you need to know what's the normal current going through the breaker, normal conditions. The other thing you need to know is that maximum voltage that this breaker is going to be exposed to. The other thing is that the maximum interrupting capability of the breaker, which means that how much current in different short circuit scenarios are going to go through this breaker. And if I go and if I run my load flow, I get the answer to the first question, which is how much current during the normal operation is going to go through this breaker. We have the answer to that question. If I go and I perform a short circuit on one of the buses in the system, then that's going to give me the maximum short circuit current going through the breaker, which is, okay, that's the interrupting capability of the breaker, and that tells me whether or not the breaker is capable of interrupting that current. One little question that we don't answer here is that if there is a transient event in your system, and if you run a load flow, you would never know the transient states that the system goes through, meaning that you might have a voltage overshoot, you might have a voltage dip, you might have a voltage oscillation, you might have an unstable situation, you might have all different transient events that load flow doesn't cover. It wasn't even designed for that. Load flow basically was designed to give you the steady state results of the system, and that's what it exactly does. When you use that tool, you always have to ask yourself the question whether or not this is what I really want to do. So again, back to the point of having the time parameter in dynamic stability simulations versus having the not having the time parameter in short circuit and load flow, that would make a big difference. That's what you get in dynamic stability you won't get in other modules. The waveforms that you see here is something that you're not going to get in other modules. But the whole thing that we started and we got to this point is that if I go back, I was talking about a step, so I can just run the whole system as you saw here, or I can go to a step and run the simulation step by step. So that was the point that I was trying to make, and then eventually we got to here. So let me just go to the dynamic stability. So all these things here, making the long story short, are your options and different options that you have that you can active, or, I'm sorry, you can choose, or you can click and choose, or you can uncheck or uncheck. And in terms of, you would say that you want them to be included or you don't want them to be included, including, let's say, do you want to have the contactor actions, or you don't want to have contactor actions? Do you want to have enable ATS action or not? Double click is another action that you can have in EasyPower, meaning that you can go, and we looked at the script here. So what you saw was one option of defining different events in EasyPower. The other option is that you can go and you can double click on a bus. Double clicking on different elements would make different sense, would create different consequences. Let's say you double click on a bus, it always means a short circuit. You put a fault there. The next question is that you would, more curious users will say, well, looking at these values here, it seems that you did have a short circuit, but it very much looks like the short circuit was removed. In terms of any option that you want to know about the double click, you go to DS options, and this is what you would see for, these are the options that you can choose, and it would make, different results for you. So if you double click here, then for a bus, let's say bus to fault, the resistance is 0, fault reactance almost 0, which means that you literally put a bolted fault current on that bus. Simulation end time 6 seconds, delay time 1 second. You can clearly see it here that as you put the fault and you double click, but the waveform very much went on for a while without showing any change or any event. So all these options are here for double click. And again, I don't go into a whole lot of details here. Right now we're just exploring different options that you can do. And there are so many differences in dynamic stability that it makes it look like even a brand new module, something that just because of the nature of the design of the module, it really makes it look very different from other modules. But if you look at it closely, you would see that this is a very good complement of anything else that we have. It has power flow in it. As soon as you switch from power flow to dynamic stability, you can see the results of the power flow. You can literally see the power flow results here. If you're not, if you want to just make a difference, or if you want to open or close a breaker, you can simply do that and see the results, because this is another double click action. So okay, it has power flow module in it. Short circuit, I can come here and create a short circuit. It not only gives me the short circuit results, but also gives me the waveforms, and it tells me what are the transient voltages, because short circuit module is gonna eventually give you the short circuit values, assuming that there is a short circuit current there, or there is a bolted fault current there sitting there forever. There is no remove in short circuit unless you go and you open a breaker. But basically, point I'm trying to make here is that those situations, they don't have a time parameter in them. They are steady. They are as if the event is sitting there forever. If it's a load flow, it's the point that your system settles to. But here you always have the option of not only running those simulations, you can, if you want, you can have the fault and then keep the fault here. Dynamic stability is going to plot all these curves for you, and if you have protection devices in your system, they will also act, and they will also trip. If if there is a case that they should trip, they would also trip. So imagine now you have a combination of short circuit on your system. You have your devices that are going to exactly operate based on a precise behavior of your waveform, and those waveforms are not going to look like a square waveform. They're going to look like the real waveform with transient values, as long as you define the models, proper models here, and on top of that you get a log here. So for every event, for all the events that you perform, you will get a log, and it tells you exactly what's happening, initialization, did it go fine or no, the command and the script, and all those results. So one way of performing a dynamic stability calculation is going to scripts. The other one is double clicking. If anything you want to change, all your double click, control, plot output, and eventually arc flash, which I get to, they all are defined here, and you can use them here. Going back to the presentation, so what we're trying to do is that induction motor starting, success, failure, synchronous motor starting, success, failure, system response to faults, critical clearing time, system response to line switching, system response to motor start. If you see, there is one thing that all these events have in common, and that is, in fact, the fact that they are transient. They happen at a certain time, you change them, you remove them, it's not something that stays there in your system. So there is always a option that for any reason that you define it or you don't define it, the system conditions change. And that's exactly in one sentence. If I wanted to describe the application of the dynamic stability or transient stability calculations or studies, is that when you are looking for system response over the time, that's when you should be coming to this module and be using it. And you look at it at the broader way, you would notice that there are a lot of calculation again that we perform every day, and we simply overlook the fact that we are just going from point A, which is the start, to point B, which is the settling point of the system. We are not looking at what happens in between. I go back to that load flow short circuit example that I gave earlier in the presentation, that you have a load flow, that load flow during the time that, let's say, a motor starts or a breaker closes or opens, there might be over voltage, there might be under voltage, there might be frequency changes that affects your system. Load flow is not going to look at it, and it's not a software limitation, it's the approach limitation, it's a calculation method limitation. Newton-Raphson or Gauss-Seidel, neither of those methods were ever designed to go and capture, let's say, transients of a system, never. So any module in any software package that you find for load flow, they are designed based on those approaches, and they're working perfectly, including EasyPower. They're not designed for that purpose. If you look at over voltage, under voltage, transient events, you have to come and use dynamic stability. We are able to determine the stable, unstable dynamic responses. We are able to determine under frequency response of system after load generator mismatch event, determine critical clearing time, evaluate load impact response of backup generator. And let's take a look at a quick example. I gave you a very quick a snapshot of, I would say a screenshot, or kind of a very short window of how the module in general works. But there is really a lot more into that, and I hope you could just follow the instructions, because I really try to start from a higher level, and then we get into more details. But in general, let me just do a quick review again. This screen here is your one line. What you put in here is not normal information that you use in load flow. It's different. Here are your plots. Here is your log messages. So if anything goes wrong, this is the first place that you have to be looking at. Whenever you run a dynamic stability calculation, you always have to come back and look at this place here and make sure that there is no error message, there is no warning message, there is nothing that it looks like a red flag. You always have to do that one. Those of you who have worked with harmonics module, you should probably know any module that we have a plot and the outputs are presented in terms of plots. We always give you the points, so it's not just the plots. You can also see the points here. And obviously there is an auto plot capability. That auto plot capability is for double click. If you double click on something like a fault here, then when you put a fault here, then for example, number one, it's gonna follow all the double click rules that you define for the system. Number two, it's gonna auto plot bunch of parameters which are hard coded in the code. It's not something that you choose, but you're more than welcome to define the type of plots that you want. For example, here when I faulted bus 1, I got the voltage in per unit, and I also got the IF in amp. So I got the fault current here, and also I got the voltage, both of them. And again, you will see that the fault was there for a while and it was removed. And I'm sure by now you would know why, because if you go to double click, you would say that fault resistance, fault reactance, delay time, fault time length. It's 0.1, just as an example. I'm gonna go here and make it 2, or let's make it 3, and then I apply it and I would say okay, and I come back here and I run it, and you would see immediate difference here. So here we will have all different options that you want to use in dynamic stability, all control options that you can see in dynamic stability, all the plot options that you can see in dynamic stability, and eventually the arc flash. So that being said, I'm going to close this one, not save it, and I'm going to close this one, not save it, and go to this example. And in our presentation, I believe there was a mention to, okay, open DS intro example file. So this is a good example. I'm going to go here, open DS intro example file, see what the presentation instructs me to do. So next step is add Siemens 500 horsepower motor dynamics data. Notice change in the motor data to symbol, and these are the change. This is very important. So this is a step by step. Now we are coming from higher level a little bit lower, and we get closer to the component level here. So we're gonna go and add the parameters for a 500 horsepower induction motor here, okay, and then we will enter DS focus. So I'm gonna escape for now, remove it, go here, and so utility, no change in data. Bus, the same thing. Transformer, nothing. But I will get to these details more, but for now let's keep in mind there are some certain modules that you need to have dynamic stability model for them in order to be able to run a successful or meaningful dynamic stability module. Let me just explain it a little bit more. You can still run a dynamic stability module or dynamic stability study on this motor. It just not give it will not give you the type of waveform that you expect. The waveforms are going to look like a square waveform because the behavior, because you didn't define a model of governor, or you didn't define a model for exciter, and those are the things that you can define in dynamic stability. You cannot define them in other modules for very obvious reasons. So I'm gonna go here and follow the instructions and go to dynamic stability, enable the motor model, and I would say let me just go back to the presentation, and it says that add Siemens 500 horsepower motor dynamics. So Siemens, let's look for Siemens here. Let's go and look for 500, and we will talk about this, but again I have to go and jump ahead of myself a lot of situations because it makes it more clear for you to follow. Induction machine, this IM is induction machine, 500 is the 500 horsepower is the horsepower of the machine, and then the rest we will go into the details, and I will talk about what really this naming means here. But I mean, at least for now you would need to know that this is a Siemens 500 horsepower motor here. So I'm gonna choose this one, and I'm gonna go, whenever you choose a model you have to click library, and from library it's gonna import all the data into your parameter table here. So for now I would say no, then I would go here, I would say generic, I would say squared, I would get it from library, generic. These, as you can imagine, very much like any other module, if you see a red exclamation sign, it means that you are not done. You still have to provide more information. These are all the type of information that you do not use them in neither short circuit nor load flow or any other module that you can think, because all these values here are gonna have to do with the time and how the component behaves over the time. So I have this one. Seems that I'm still missing information here. I do a squared. I import them from the library, and seems I'm okay here. I go to short circuit, everything okay here. I don't see a red flag. I am going to say okay and close it. You notice the change in the symbol. So now I have the proper model, the first step in order to go and run a dynamic stability calculation, a dynamic stability simulation. So let me just go back to my simulation, to my presentation here, and I go here. What it's telling me is that, okay, enter DS focus, right click on the motor breaker, select open and resolve power flow. Double click on the motor breaker, review motor start results, note auto plot capability, and save the system in a new file and call it DS intro example 1, which becomes the next example. But I'm gonna go back here. I'm gonna remove this guy. I'm gonna zoom out and go and right click on the motor breaker here, and we have to first switch to a stability module. So I switch to a stability module and I go here. As the presentation instructs us, is that open and resolve power flow. This is another capability of dynamic stability that, let me just make this claim here, that if you use the dynamic stability module, you very much have covered any application that you would need when you do your simulation in PowerFlow, except for the fact that you always have the opportunity to use and import the dynamic stability values and also look at the waveforms. But if not, if you just want to start and if you just want to have a snapshot of the steady state values, look at here, open and resolve power flow. So basically what happens here is that it opens the breaker and gives you the power flow results. Now you would say, well, okay, I need to see the results, the format or the way that I like to present them. The way you would do that, you can just go to the bus. These are simply the power flow options that you have. Let's say that if you're interested in the currents, you can go and say, I want to see currents in ampere, and you would apply and you will see. So this is basically the point I'm trying to make, is that this is your load flow module with a lot more features to offer, because right now I just ran it for load flow because maybe I was in a hurry, maybe because you just wanted to see how it looks like if the motor is offline. But let's not forget that any moment of time I can go and double click on this guy and run a short circuit and see the waveforms. I can do that. I can anytime I can go back and run. If I decide to run a script or define a script, I can go define a script and run it. But you have to keep in mind that now we have a lot of dynamic stability parameters here, which allows us to do that. But I would say a lot of applications of the load flow and short circuit are completely covered in a lot more, or in a broader way, meaning that, again, I ran my load flow here with this breaker open or this breaker closed, and if I was just curious to see that what happens during going from point A to point B, I just double clicked on the breaker and it took me from point A to point B. What you get from load flow is here, these points. When the breaker is closed, you would get these values here. What you get from the load flow when the breaker is open are these values here. But what you don't get, and you might be missing, is how it goes from this point to this point. That is dynamic stability. So I think that by now it should have been very clear for all of us that what is the need, why we should go and switch to dynamic stability when we run what type of a study. So it really, I can give you numerous examples. Let me just mention that faults, different transient faults, motor starting, governor and exciter test, load shedding, load additions, any other type of transients, including, let's say, faults that trip a breaker. So meaning that you have a fault, but you don't open a breaker. You let the system decide if the breaker opens. All those transients can be captured in dynamic stability module. So right-click on the motor breaker, select Open and Resolve Power Flow, double-click on the motor breaker. We did all those things, and we eventually have to save it as an example one. Now, there is another example with generator addition. So this time, obviously because of the time limitation, I hope that I just talked enough about the importance of dynamic stability simulation, because the whole purpose of this 1 hour, or we might go slightly beyond 1 hour, is that I wanted to address the fact that why this module was designed first place. Obviously we had feedbacks from users that they asked us to include this type of studies. That was reason number one that we included it. Number two, what would be the now we might have some users that will say, well, I have purchased, or I have the software, or I have bought the dynamic stability license. I just don't know where should I use it. This is the type of applications that you should be using it. If you have a governor model, if you have an exciter model, you can't model it in any other module. The only way that you can model it properly is dynamic stability. So let me just go back, because it might not be completely covered. Obviously, for many reasons, we will have more of these webinars. This is just the beginning. I have always been teaching these classes, and I would like to kind of increase the knowledge and interest, and also reach out to those users who don't know we have this module, or they are dealing with some type of difficult applications, but they can't find their tool or the good tool that can provide the results for those type of studies. And this might be a good match if they perform those type of transient studies. Let me open up okay, we don't have a generator here. So what I'm gonna do here is that I'm gonna exit, and I'm not gonna save it. So I'm not saving any file, and I go to the other file which I already have it ready here, and I wanted to show some stuff about the some editor pages. Motors and generators are the most important elements, components in dynamic stability. You have to make sure that you define proper models for them. Here, this is an example. It's a ready example. So number one, you have to check these checkboxes, and you have to enable the generator model, you have to enable the exciter model, you have to enable the governor model. They all have to be. And look at the extent of the information here. Look at how much information we have here, including the transient time constant, subtransient time constant. We use a DQ model for the induction motors here. It is a generator. It is a synchronous generator here, but we use a DQ model for both of them in general for machines, for induction and synchronous machines. And you can see all these parameters. Again, I have to really emphasize that there are a lot of information here, and you would get exactly the type of precise, if you're interested in precise response or voltage or currents of a system, that's the way to go. You should start putting these values in your dynamic stability module, and then and simulate it and look at the results. So we don't have a PSS here, so I'm not going to activate that one, but this is another example. So I go back to so this is just wanted to make sure that a screen editor page of the generator and the type of information that you have to enter. For motor, we did the example together. We will go back and revisit it, but here very similar. You have to enable the motor model, you have to and then also you have to choose models for your starting load and for your running load. So the software is gonna go and choose these values right at the start of the motor, and then when it goes into running, then it uses these values. And these models and these curves are the torque versus the speed, or torque versus the slip. And those of you who have more information or more knowledge about the induction machines, you know that torque versus slip is one of the very first type of information or data or curves that you would receive when you buy or you start using the induction motor in your project. So you should have those values. If not, we have a library, we have a very extensive library that provides different modules, different models, and you can use it here. And I will get to more details of these elements here, of these components here, in future webinars that I would do. So I'm gonna close out. I'm gonna go back here and let's take a look. Follow the steps to get set up for a simulation. Run a power flow to make sure everything is okay. If okay, say I already did that. Enter the DS focus. Click on define plots toolbar button and add channels for 480 volt bus voltage, generator speed, generator mechanical power, generator current, and motor speed. Click on OK. Plot definition dialog. So let me just remove it again from this screen. Take it to my other screen and go back here. Number one, let's look at the power flow results. Everything looks okay. So you didn't have to do that, but we always recommend to do that before going to power flow, before going to dynamic stability, because dynamic stability, as soon as you switch to the module, it does run the power flow automatically. It's not something that you say yes or no. It does it for you and it displays the results right there. In order to get better results, it's not necessarily recommended, but I mean that you don't have to always do that, but we recommend to do that because it helps you to get better, more precise answer for some very specific cases. Not every case, but there are cases that if you run your power flow first and you switch to dynamic stability, it would help the program to give you more precise answers when you or results when you switch to dynamic stability. But regardless, I switch here. You know, let me just bring it here and read it so that we can read it. Run a power flow. I did that. If okay, say okay. Enter the DS focus. Click on define plot toolbar and add. So one of the things that maybe we didn't spend too much time on it is the plots. So I'm gonna go and define plots and just follow, you know, it's all the instructions in that in our slide. It says that add the plots channels for 480 volt bus voltage. So for it is bus 1 and it's already here. If you look at the drop down list, you would see, and I'm pretty sure it's pretty impressive, that the extent of different values and parameters that you can plot. If you really, let's say that you're modeling a power plant, it's a large power plant, and you would like to see that, you know, addition of a generator, or just when you bring a generator online, how it's going to impact the rest of the system. This is how, and this is where you can see literally any type of parameter that you like to plot. And let's keep in mind, it's not a final result. It's a plot. So you can just literally look at the, let's say, fault current, you can look at the bus angle, you can look at the frequency. And for those of us who work with power systems and modeling of power system, you know that when you run a load flow or when you run a short circuit, you would never consider the frequency of a system. If you have prepared maybe short piece of code, you know how difficult it becomes when you bring in the frequency into elements of a power system, because all the reactances and all the impedances, anything that has a F factor in it, including, let's say, capacitors, inductors specifically, they are going to change with the frequency. So the frequency goes up by, let's say, 30%. The value of X is going to go up by 30%. And we don't cover it in load flow. We don't cover it in short circuit. Naturally, no other software package does it if it's just a normal short circuit, because, and I don't want to kind of talk about, other packages in the market. Maybe let me just limit it to just a kind of a general statement here that load flow approaches or load flow algorithms, where they were never designed to consider frequency. So the point is that you can have the frequency and the system is modeled and the frequency is modeled, and you can go and see how it changes. So I cancel out. so that I don't change it, I go back here. So one of the so add plot channels for 480 volt bus voltage. So bus voltage here, and DS motor here, and motor speed. So generator speed, generator mechanical power, let me just look at here. Here we go. Two bus voltages are here. Then mechanical power, generator current, and motor current, all are here. So what I can do is that basically I can cancel out because I don't want to change them. I am actually going and get the example ready here, the one that I have performed, and that is here, this example 2. And look at the dynamic stability. There are some certain steps that you don't see, and because of, again, time limitation, I have prepared these files. They are ready to go, and we will have webinars which I will go into more details on how I prepared them. But one of the facts is that if these symbols are showing here, it means that I already input the dynamic stability parameters and numbers in here. So the other thing is that the plots. So I go to dynamic stability, and the plots are already defined, but you know, I can maybe have the presentation again here. This is the list of items that we wanted to plot, and let's go back. Bus voltage is here, as you can see. The dynamic stability generator speed is here. Dynamic stability generator mechanical power is here for generator 1. Motor speed is here. All the values are here, and when I go and let's say I put a fault in here, it defines this value. Obviously you have to go back and look at the plots. I defined plot 1. This is the auto plot capability that we talked about. So I'm gonna go to plot 1. Everything that we defined is here. A few points that this is a lot of characteristics that dynamic stability and harmonics modules share, because they both have plots in them as one of the output formats, and you can see all the parameters that you plot here. You can see the values here. You can just right click, format data, view data. You can go here, and you can, there are all these data, you can sort them, you can copy them, take them to another software, maybe you can take them to Excel, you can copy. So all those capabilities are here, and you can just, you know, work and do all the cosmetic changes that you want to do on the data. I don't want to focus on that one. There is so much important and so many important features into dynamic stability that I don't want to kind of spend a whole lot of time on this, but we can certainly talk about it too. So I go on these waveforms here, and I would say, let's say I want to see the exact values. So I choose the data cursor, come here, and as you can see, the values all are showing here on this corner, and you can even move this guy to somewhere that is more visible. So let's say the blue line here, as you can see, is maybe a little bit you know, kind of a square sign. So this is this one, that's bus 1 voltage in per unit. Then the red one is generator 1 speed per unit. Then this shape here and this color here, I look for that, and I see that it's generator 1 the current in per unit. And finally the last one, which has 2x sign at the end of a kind of a I would say bright blue color, and that is this guy here. It's the speed in per unit of the generator. So it's very much, you know, the first thing that I would, if I wanted to see whether or not this system is stable, I think all of you guys can just answer that question right away. Is that is this system stable? Yes, they all are going to assist it to a point that I don't see oscillation. So that's number one. Number two, what is the maximum voltage, let's say for bus 1. You can just go and see, okay, this is my bus. It seems that I have a huge voltage. Well, I have a voltage drop here. After my voltage drop, I see oscillations in the generator 1. Generator 1 green, this guy is generator 1 mechanical power in per unit. So all these oscillations are, so if you're interested, let's say what is the maximum of this waveform, you would choose here, come here, and you read the maximum value here. So that being said, let me just briefly, we looked at 2 or 3 examples. Let me briefly bring our simulation and our work to end and speak about the conclusions. So in this presentation, basically we spoke about dynamic stability and its application. We talked about that, why do we need to use a dynamic stability module in general. Dynamic stability module, you would always use it to capture anything, any waveform, any change, any transient event that depends on time, and you're interested in those changes over the time. As I went over a few examples, you can run a load flow. It's going to give you the final results or the steady state point of your system. If you run a short circuit, it's going to give you the final results, and it's maybe for short circuit, I don't know if this is the exact good technical term, but it gives you the result as if the short circuit stays there forever, and it gives you, how much short circuit is going to go through different sections of your system. When you go to the when you go and you use dynamic stability, it would be able to capture those changes and give you the how you go from point A to point B, how much waveforms are gonna change, how much voltage drop you have, or any changes that you might have in going from point A to point B. Would you even damage some of your system components? So all those answers, all those questions can be answered through dynamic stability module. So that being said, let me find the presentation here that will cover that part. So I go here and I open it up, and we go to examples, the derivative, and yeah, okay, let me bring it here and go back to the first page again, that when do we need dynamic stability studies and examples, and maybe arc flash was one of the options that I didn't quite cover. So in order to cover that one, before I just conclude our presentation here, let me just go back here, talk about this arc flash. As you see here, the arc flash simulation in dynamic stability would very much be similar to any other short circuit module, except for one difference, which might be very important for some of our users. When you run a short circuit in other modules, the change of a current would be a square change. So you have a short circuit, the current goes up. If there is a trip, the current comes exactly down. It goes to zero straight, unlike these waveforms. So when we run arc flash, we use a method which is called integrated method. That integrated method is going to look at all different components and anything that drops out. Let's say, let me just give you an example. For example, if you have a fault on this bus here, and the fault current, let's say from this generator is ongoing, it's going for a while, and before that this breaker, because of the amount of the short circuit, this breaker opens. So integrated method is gonna go and look at the decay of this current and integrate it over the time, and from the time that you have a fault to the time that the fault contribution, entire fault contribution goes to zero, it's going to account for all those changes, including the breakers that drop out, some of the motors that stop contributing. So if you have a motor and you have a fault here, if the fault goes on for a while, the voltage on this bus is gonna go to 0. And if this goes to 0, the current contribution from the motor is gonna go to 0. And dynamic stability is gonna go and calculate, actually look at the current and how it decays to 0, and integrate that area underneath the current curve and calculate that incident energy. So for those of you who are familiar with our integrated method in short circuit to calculate the arc flash, this is the same method that we use here. I may describe it or go into more details in future examples, but one thing that I can describe, one thing that I can say here is that if the curve or if the current goes up and down because of a breaker opening or breaker closing, these type of waveforms, these are going to be considered in arc flash calculation, incident energy calculation, unlike short circuit or other modules that they look at the current going up and coming down like a square wave type of approach. Now, that being said, let me just activate arc flash simulation here. Click apply, click OK, and then put a fault here just to see what EasyPower is gonna generate for us. As you see, the results, the bus 1 was faulted, fault was removed. You would say, well, we didn't remove the fault, but if you remember, we have a section that we define all the double click actions, and this is where it comes from. So after 1 second it was removed, simulation was run up to this seconds. This is the incident energy. The bolted fault current, we don't use that famous 85% rule for low voltage currents. You can go and change it if you want, but this is based on the 100% bolted fault current. This is arc flash energy, this is the time before the breaker trips, boundary, and arc flash PPA level, which, you know, according to 2015 NFPA, in fact, this shouldn't be presented. You would need to either use the for this one we have gone with the previous versions of NFPA, but doesn't matter here. You have the incident energy here, and that's what you want to kind of get as per NFPA 2015. So that's how we show the results, and nothing else here is going to change. So basically what I did in this presentation was that I introduced the dynamic stability module. It has a lot more to offer. 1 hour time gave me a chance, gave me opportunity just to describe that what type of studies, what type of work you can do in dynamic stability, how it can complement other type of studies that you do. And in future I will put more presentations and other presentations together which describes the details and how to input the values for governors, for generator, exciter, and all those different components. Thank you very much. Have a good day, and bye.